So now let us consider the so-called uniform topology on the set of all functions from x to y, but we specialize to the case when y is a metric space, and we will define it. We will define the uniform topology as a metric space itself. So we will define a metric on the set of all functions using the metric on y. So for this, consider the so-called bounded metric on y, which is given by the d bar notation. So d bar of 2 points y1 and y2, this is the minimum of d y1 y2 and 1, the number 1, and it is known, right, and I also gave this as an exercise before, that the metric, so first of all, the d bar is a metric function on y, and the second more crucial thing is that d bar gives the same topology, same metric topology as d. So in the notation that we used before, so tau d bar is equal to tau d. So this is the bounded metric corresponding to a given metric, which gives the same topology as the given metric. And now we define the so-called uniform metric, on f and xy, and this is defined as follows. So for f and g belonging to f and xy, so f and g are functions from x to y, need not be continuous, arbitrary functions. We define the function rho bar takes into as input two functions f and g, and this is defined as the supremum of all the values d bar fx and gx. So remember that f and g are functions from x to y, so fx belongs to y and gx also belongs to y, and now we can use the d bar metric to get a distance between these 2 points, and we take the supremum of all such things when we vary the point x in x. So this is the definition of the uniform metric, and I leave it to you as an exercise to show that this function rho bar is a metric function on f and xy. So using the fact that d bar is a metric, you can show easily that rho bar is also a metric. Okay, so now that we have a metric, we can define a topology induced by that metric, and this is the so-called uniform topology. Uniform topology, and this is the topology generated by the basis, which is basically the basis of metric balls. So b rho bar f epsilon, so f belongs to this space of functions and epsilon greater than 0. So this is a collection of basis elements, and this topology generated by the by this basis element of the epsilon open metric balls with the metric function rho bar and arbitrary center and arbitrary epsilon, and this generates the uniform topology, is called the uniform topology on Fn xy. And so this is nothing but this is the metric topology, which we can denote as tau rho bar, defined by the metric rho bar. So what kind of functions are allowed in this metric ball? So let me draw a picture, and I hope it makes it clear. So suppose that epsilon is less than 1, because we just want to consider small metric balls, and in this case d bar of y1 y2 is equal to d bar of y1 y2 less than epsilon is equivalent to d y1 y2 less than epsilon. So if epsilon is less than 1, then d bar is simply going to be d. And for such an epsilon, suppose that we have a function. So for example, if y equals r2 with the Euclidean metric, then any function from, let us say, from 0 1 to r2. So this is our x now, and this is our y, and this is given by some graph. So this is any function, but let me draw a continuous function so it may be easier to visualize. So let us say that f is a continuous function. So this is f, the function f, and this is basically the graph of the function. If you want, this is the function is a path in the space R2. And now what we do is we take width, kind of a tube of width epsilon. So this distance is epsilon around this path. So everything is epsilon, and we can draw a kind of a tube like this, something like this, and any function which has which is a path. So g is also a function between these two spaces, and the function g may look like this. So g always lies within the tube of this between the upper and lower blue lines, blue curves, and in this case we have that rho bar of f and g is less than epsilon. So basically this tube is the metric ball with center f and radius epsilon. And if any function has points outside this blue curve, so suppose that we have another function like this, let us say g prime, then g prime does not belong to this metric ball. So we see that the uniform width, so this is why it is called the uniform topology. This is because we are taking a uniform width at each of its points, each of the points of fx, of the image of fx, and considering the metric neighborhood around these points. So this is a visual interpretation of the uniform topology, and the main theorem of a uniform topology is the so-called uniform limit theorem, and for that we need the concept of uniform convergence of functions, and this you might have seen in an analysis course, and here we will use the topologies to define, rather the metrics to define uniform convergence. So here is the definition of uniform convergence of a sequence of functions fn. So all these fn's belong to fn xy, and so does fn xy, and here of course y is considered as a metric space. So this definition requires Y to be a metric space and uses the metric on Y. So the definition says that the sequence Fn converges uniformly. So this is the main part about uniform convergence to a function f if given any epsilon greater than 0 there exists a capital N such that the distance between Fnx and Fx is less than epsilon in the metric D on Y, and this holds for all all points x in X and for all n small n greater than or equal to capital N. Now the difference between uniform convergence and what is called pointwise convergence. So this just says that Fnx converges to Fx for all x. So this is the pointwise convergence, and the difference between uniform convergence and pointwise convergence is that one can choose capital N independent of any point x in X in the case of uniform convergence, but n depends on x on a chosen point x in pointwise convergence. So this is the main difference between uniform and pointwise convergence, that when you are going to choose a capital N for which your convergence criteria holds, in the case of pointwise convergence, that capital N will depend in general to on the chosen point x. So here this Fn of x converges to Fx, so you have already chosen a point for the convergence and your capital N will depend on that point. However, for the uniform convergence, this capital N works for all x in X. So this condition holds for all x with the same N, and this is the part that I wrote here, that N is independent of any point x, and this is the in other terminology we say that it is uniform over X. So this is the reason why it is called uniform convergence. And the relation between uniform convergence and the uniform topology, which I can write as a theorem, is that a sequence Fn converges to F in the uniform topology on Fn xy if and only if Fn converges to F uniformly. Okay, so they are basically equivalent. The convergence in the uniform topology and the definition of uniform convergence that I just gave, they are basically equivalent. So I leave this as an exercise for you to prove. Of course, if you have any trouble, you can always ask me in the discussion forum, and this exercise isn't that difficult. And the main theorem that I mentioned about the uniform convergence is the following theorem, which is called the Uniform Limit Theorem. So this is the statement of the Uniform Limit Theorem. It states that if you have a sequence Fn of functions, but now each of these Fn's is a continuous function. So this sequence is a sequence of continuous functions, and the assumption is that it converges uniformly to some function f, then f is also a continuous function. So if in general we don't know whether a sequence of continuous functions converging uniformly within the set of all functions is continuous or not, but this statement guarantees that when you have a uniform convergence, then the limit of the sequence is, which is a function from x to y, is a continuous function. And said differently, so in other words, we can say that the set of continuous functions as a subset of the set of all functions is closed in the uniform topology on Fn x y. So here also, by the way, here I'm again assuming YD is a metric space, otherwise this definition doesn't make any sense, because I defined only uniform convergence is defined only in terms of the Y being a metric space. So here I am just rephrasing this result, and it says that the set of continuous functions, which is a subset of the space of set of all functions, and this is closed in the uniform topology on Fn xy, and this is just a consequence of the sequence lemma that we proved for about convergence of sequences, and there the metrizability of the space played a role. And here, of course, in the uniform topology, these are metric spaces, so you can, the sequence lemma gives an if and only if condition, and it says that subset is closed if and only if the limit of every convergent sequence belongs to that set. So here we are saying that given any sequence within the set of continuous functions cxy converging to some point in the uniform topology, which means that, which is the same as saying that the convergence is uniform in the other definition that I gave, then f is a continuous function, so the limit is also in this set. So this is precisely the same as saying that it is closed in the uniform topology. So let us look at a proof of this theorem. So we want to show that f is a continuous function, and this is the same as saying that given any neighborhood f of, let's call this neighborhood v of f of x. So given x and any neighborhood v of f of x, there exists a neighborhood u of x such that if x prime such that f of u is a subset of v. So we have seen this definition of continuity, and we have shown that this is equivalent to the open set definition, which said that preimages of open sets are open, and this is the same as saying that given any epsilon greater than 0 and x in x, there exists a neighborhood u of x such that x prime belongs to u, implies that the distance between f of x and f of x prime is less than epsilon. So it is not very hard to come from the second line to the third line, and I leave this to you as an exercise. So as a hint, take v to be an epsilon neighborhood of fx. Okay, so we are going to prove the third statement, and for this we note that from the triangle inequality we have that the distance between fx and f of x prime is less than or equal to the distance between fx and fnx plus the distance between fnx and fnx prime plus the distance between fnx prime and fx prime. So we are splitting this distance into three parts and using the triangle inequality twice to get this inequality here, and this is true, holds for all n, because this point f of n x and fnx prime is arbitrary, so it holds for all n. And the idea now is to use the uniform convergence. So let me write the first term as 1, the second term as 2, and the third term as 3. So the idea is to take the first and third term, make it smaller, make them smaller than epsilon by 3 using a uniform convergence, and 2 make it smaller than epsilon by 3 using continuity of fn. So in this way the sum of all these three, epsilon by 3, epsilon by 3 and epsilon by 3, will be less than epsilon. So how do we use a uniform convergence for 1 and 3? Well, this is just the definition of uniform convergence. So fn converges to f uniformly is the same as saying that given epsilon greater than 0, there exists a capital N greater than or equal to capital N belonging to the naturals such that the distance between fnx and fx is less than epsilon for all x in x and n greater than or equal to n. So we choose epsilon prime to be epsilon by 3, then there exists a capital N such that this condition holds for all x in x and all n greater than or equal to capital N. So this holds, and now we use the continuity of fn and we restrict to n greater than or equal to n. So then this implies that there exists a neighborhood, a u of x, so continuity at x, and so this means that there exists a neighborhood u of x such that if x prime belongs to u, this implies that the distance of fnx and fnx prime is less than epsilon by 3. And so now we choose this neighborhood u and choose a small n greater than or equal to capital N in the triangle inequality. So we get for x and x prime belonging to u and n greater than or equal to n, we get that the distance between fx and fx prime is less than or equal to d of fx fnx plus d of fnx prime plus d of fnx prime fx prime. And remember that the first one was less than epsilon by 3, this was less than epsilon by 3, and the second one was less than epsilon by 3. This was the terms 1 and 3, and this was the term 2 above, and 1 and 3 were less than epsilon by 3 due to the uniform convergence, and the second one is because of the continuity of all functions f of n, and therefore we get this continuity of f. So this means that f is continuous. So this is the uniform limit theorem. Notice that if we only had pointwise convergence, then you cannot choose the same capital N for both 1 and 3 because they are over different points x and x prime. So because this capital N will depend on the chosen point, and therefore we cannot choose the same n, and this is the reason why this argument works, because we have chosen a uniform convergence rather than pointwise convergence. And now let me end with some remarks regarding the uniform convergence. So the first remark that I want to make is that the uniform topology is in general finer than the topology of pointwise convergence, and strictly finer when x is infinite. X is an infinite set. As a set, it is infinite, and it is also a topological space, of course. And this is I leave this to you as an exercise to come up with when x is infinite, come up with open sets in the uniform topology that are not open in the topology of pointwise convergence. The second remark is that if fn is a sequence of continuous functions converging to a function f in the topology of pointwise convergence, then f may not be continuous, And a standard example for this situation is when you take fn, so x and y are taken to be the compact set 0, 1, and fn from x to y is defined as fnx is equal to x to the power n. And so the graphs of these functions, so let me draw some graphs here. So this is the point 0, 0, this is the point 1, 1, and for n equal to 1, well, for n equal to 1 it is just the straight line y equal to x. For n equal to 2 it's a parabola, so it is something like this. For n equal to 3 it is some flatter curve like this, and for higher ends it goes closer and closer to the vertical line at x equal to 1. And so this I claim without proof that fn converges to the function f, where f of x is equal to 1 if x equal to 1 and 0 if x equal to 0. And this is basically because of the fact that if you have any value between 0 and strictly less than 1 could include 0, then r to the power n converges to 0. This is a well-known fact in analysis, in calculus, and this is for all n greater than or equal to 1. And however, for the point at 1 to the power n is equal to 1, so that has to be fixed. So this point has to be fixed, but all the other points go to 0. So all points here go to 0. So we have a topology. In the topology of pointwise convergence, there is a convergence of fn to this function, and of course this function is not continuous. F is not continuous at x equal to 1. So you see that we can have a sequence of continuous functions converging in the topology of pointwise convergence, and but the limit of this sequence may not be continuous, and this is the usefulness of the uniform convergence theorem or the uniform limit theorem, which says that when you have rather a sequence converging in the uniform topology, then the limit has to be continuous. So this is a very useful result in an analysis, and it is used all the time. So it is a nice theorem to know.